Swayam Prabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the course Advanced Thermodynamics and Combustions, which is first module, that is review of thermodynamics, and in this module we had 3 lectures. First 2 lectures we have covered, and it was based on temperature and zeroth law of thermodynamics. Second one was work and heat transfer, that is first law of thermodynamics. Now we are going to look at the second law of thermodynamics, which is mainly based on heat engines and refrigerators or heat pumps. So, in this particular lecture we are mainly concentrating on the following topics, that is conversion of heat and work, then second law of thermodynamics, then it gives the concept of reversibility and irreversibility. Then moving further, the ideal cycle for conversion of heat to work is the Carnot cycle. We will try to explain what a Carnot cycle is all about. Then in the last segment, which is the most important inference of Carnot cycle, that is the interpretation of absolute temperatures, and that we can do it through analysis of thermodynamic temperature scale. So, let us start the first segment of this lectures, that is the conversion of heat and work. So, from the first law it says that the work and heat, they can be related together by these equations, that is dq is equal to du plus dw, where work transfer and heat transfer are equal when these processes are taken place in a cycles. At that point of time your internal energy is equal to 0. So, what we can write for a cycle, we say dq is equal to du plus dw, and here dq is your heat interactions, dw is the work interactions, du is the internal property of this system. Now, when in a cyclic process, what happens, the starting point and end point remains same. So, there is no change in the internal energy. So, we can write q cycle is equal to w cycle, and also we can this equation also says that w cycle is equal to q cycle. So, these two equations has, although they are meaning wise they are same, but in terms of interpretation of heat and work they are little bit different. So, what it says is that first law does not distinguish between the work and heat, but they are interpreted as a energy, and when you say w cycle is equal to q cycle, it means that complete conversion of work cycle, complete conversion of work to heat is possible. But in other words, ideally speaking, we can as well say that complete conversion of heat to work is possible, but here the first law does not distinguish these equations. Now, here we have to make a pause, saying that why whether we can write this both the equations in a correct way or not. So, this turns out to be the interpretation of second law. So, in a sense that when you say heat, so it is by virtue of temperature difference, and when we say work, it is interpreted as the displacement under a action of force. So, many times we view this as a rising and falling of a weight. So, just to make some summary of conversion of work to heat. So, in general we can say work of any kind may be done on the systems in contact with the reservoirs, causing heat to leave the systems without altering the state of the systems. So, it is apparent from the first law transformation that work to heat can be accomplished with 100% efficiency, that is W is equal to Q, and this process can be continued indefinitely. That means, complete conversion, this process can continue, that means as long as we have work available to us, we can keep on converting it to heat as long as it is available to us. But the opposite process, that is conversion of heat to work completely and indefinitely is not really true, even if the first law is satisfied. For example, we can say in an isothermal expansion process, of course, there is no change in internal energy because there is no change in the heat transfer. We can say Q is equal to W, and the process involves change of state of the gas, which means that means in isothermal expansion temperature remains same, the volume increases, pressure decreases. But this continual decrease of pressure is possible till one particular point. For example, in this case the downstream atmospheric conditions restricts this expansion process. That means, pressure can be decreased continuously to the dead state atmospheric conditions. So, in other words, we can say that isothermal process cannot continue indefinitely, it has to stop somewhere. So, this is the conditions that first law does not identify this concept. So, in a thermodynamic viewpoint, we can say that there may be series of processes through which the system can be brought to its initial state, that is cycle, and each process of the cycle involves the involvement of work flow and heat flow from the system and the surroundings. So, the work interactions or heat interactions can occur between two reservoirs which are maintained at two different temperatures, one at higher temperatures, other at the low temperature of the system. So, this concept was told that when if you want to transfer the work interactions from heat, then you have to view it as a cyclic process that should occur between two temperature limits, that is at high temperature and lower temperatures. And the absolute values of work and heat transfer is based on the type of feasibility of the formulation of our requirement. So, this gives the concept of heat engines, refrigerators or heat pumps. Now, from the second law, which we will be talking later, that when you talk about conversion of heat to work, it is accomplished through a device or you call it as a cyclic device, and in our term we call this as a engine. So, this engine could be an internal combustion engines like petrol engines, diesel engines, or any kind of external combustion engines like steam engines, or we can have refrigerators or heat pumps which consume work. So, all these things we are going to explain subsequently. Now, how this conversion of heat to work is possible? So, here we have explained about the concept of heat engines, then we have refrigerator, then we have heat pump. So, the first figure says that there is a high temperature reservoir at TH, there is a low temperature reservoir at TL. So, and we have a heat engines, that means in order to transfer in order to have a net effect of work transfer from heat to work, then we must have introduce a cyclic device, and this cyclic device we call this as a heat engine. It must takes QH amount of heat and reject QL amount of heat to the low temperature reservoir. So, in the process, if you can just look into its first law analysis, then we can say net work is nothing but difference in the QH and QL. And from this we can also derive the expressions for efficiency of these heat engines, that is nothing but ratio of Q net by QH. So, this turns out to be efficiency of this heat engine is 1 minus QL by QH. So, this is one concept where we call this as a power producing device, where work comes out of the systems. That means, work is done by the system. Now, in other situations, other two situations what we have is that work is being fed into the systems, and side by side if you do this, then this particular cycle, heat engine cycle, can be reversed. One is, that means heat can be taken from the cold refrigerated cold space, and it can be rejected to warm environment. So, in this case, when if our design in other situations also similar concept is there, but that depends on the, in both the cases we have the required input is W net, but the desired output is different. If you are concentrating on the desired output as QH, then such a philosophy we will call this as a heat pump. If your desired output is your QL, that means QL is the essence of your requirement, and so we call this as a refrigerators. So, based on this we derive the expressions for coefficient of performance, that is QL by W net. So, same expression we can use in the other in a different form, that means QH minus QL is nothing but your W net amount of work which is done onto these systems. Other concept we can use it COP as QH by QH minus QL. So, this is the three situations where we have demonstrated that how conversion of heat to work is possible, and these concepts leads to the fact that is called as second law of thermodynamics. So, this when you talk about the second law of thermodynamics, there are two possibilities or two important statements. One is Kelvin Planck statements, other is Clausius statements. So, let us talk about the first statement, which is Kelvin Planck statement, and it is based on the concept of heat engines. So, essentially we have a high temperature reservoir, we have a low temperature reservoir. So, if a heat engine has to operate in a cyclic manner, then we can say the heat engine takes QH amount of heat and rejects QL amount of heat to the low temperature reservoir, and side by side we get a W amount of work. Now, one interesting one of the interesting feature is that when you say that the process has to occur in a very slow manner, then we can view these particular things as a reversible processes. So, what we can have is that when you take this amount QH amount of heat, we assume that temperature of hot reservoirs should not drop. That means, this particular temperature TH of the hot reservoir remains as it is, and the process has to take place in an isothermal manner. Similarly, when we reject the heat to the low temperature reservoir, that is TL, then the temperature of this low temperature reservoir should not change. All these processes has to occur in a isothermal manner. So, that is what we say, there is some processes or series of processes during which heat is absorbed from the external reservoir at higher temperatures. There are some series of processes that occurs for which the heat rejection takes place external to the external reservoir at low temperatures. Now, here and in this process what we can say, based on the first law, we can say cyclic heat transfer Q cycle is equal to cyclic work transfer, that is W cycle. And one of the important thing is that if here I will try to say that if there is no change in the internal energy, then we can say that the first law is satisfied, that means Q cycle is equal to W cycle. But what imposes the second law? Is it possible that all the Q cycle is equal to W cycle? So, here the second law imposes the conditions that W cycle should be less than or equal to 0. So, in other words, we can say that this W cycle either can be 0 or it can be less than 0. So, less than 0 means that some part of heat must be rejected to the low temperature reservoir. So, with this condition of impositions, we can write the second law of statement in a negative form, that is, it is impossible to construct an heat engines that operates in a cycle and will produce no effect other than the extraction of heat from a reservoir to perform an equivalent amount of work. Now, again this second law of thermodynamics can also be interpreted in another way, and we call this as a Clausius statements. So, in a Clausius statement, if you recall our concept of refrigerators or heat pump, we say that the QL amount of heat is rejected from the is taken by the refrigerator or heat pump from the low temperature sink, and it is rejected, and this refrigerator or heat pump rejects QH amount of heat to the heated space or warmer environment. So, that to do this we must provide some of the net work input into this cyclic device. So, that is W net. Now, if you say this is the actual concept of converting heat to work or taking heat from low temperature sink to the high temperature source, which means that it must take some W net amount of heat to perform this change. That means, to reject this QH amount of heat to the warm environment. So, based on that, we can also imagine in a similar way. What it says is that we have a refrigerator or heat pump that takes W amount of heat and W amount of work input, and while doing so, when it takes this W amount of work, then it can take QL amount of heat from the low temperature reservoir, and it can reject the QH amount of heat to the high temperature reservoirs. The high temperature reservoir is maintained at TH and low temperature reservoir is maintained at TL. And of course, in a similar sense, we can also view that process has to occur in a very quasi-static manner, and mostly it should be in isothermal process, so that the temperature of the reservoirs do not change. And since there is no change in the internal energy, so that heat rejected to the high temperature reservoir is always larger than the heat extracted from the low temperature reservoir by an amount of work done onto the systems. So, this frames the basics of the negative statement of second law, and that is commonly known as Clausius statement. So, what it says is that it is impossible to construct a refrigerator that operates in a cycle, and it will produce no effect other than the transfer of heat from the low temperature reservoir to a high temperature reservoir. I need to emphasize here the fact that the Kelvin Planck and Clausius statements are negative statements, and they has to be written in this particular manner. And whatever may be the consequence, whatever may be the interpretations of Kelvin Planck or statement or Clausius statement of second law, one thing is ensured, that both of them are the statements of second law and they are equivalent to each other. That means, if some system violates Kelvin-Planck statement, then it must also violate Clausius statements, and if some system violates Clausius statements, it also should violate Kelvin-Planck statements. Here I have demonstrated the fact that how a refrigerator and heat engine that acts together, they violate the Kelvin-Planck statements. What I can say here, that we can initially view that this you can say that as if we can think about a refrigerator that takes QL amount of heat and also it rejects QL amount of heat to the high temperature reservoir, and in this process there is no work done in the systems. So, this violates Clausius statements. Now, side by side we can also construct another heat engines that takes QH amount of heat and rejects QL amount of heat. So, in this process it does the W amount of work, which is nothing but the difference between QH and QL. Now, if you take together both heat engine and refrigerator and they operate in this manner, it can be viewed that a system takes some QH amount of heat and rejects and gives a W amount of work, but that means this will violate the Kelvin-Planck statements. Similar logic also can be applied for situations where heat engine and refrigerator they act together and they violate Clausius statements. Now, after this, let me talk about some of the inferences that we that are dealt from the second law of thermodynamics. So, this second law of thermodynamics is not a deduction from the first law, rather it stands itself as a separate law of natures. So, it puts the upper limit of any kind of devices that takes some amount of heat to convert into work. So, it means all the heat cannot be converted to work completely and indefinitely. And in a layman's sense, we can say that the first law denies the possibility of creating and destroying the energy, while the second law denies the utilization of energy in a particular manner. So, any device or machines that violates first law is known as perpetual motion machine of first kind. Any machine that violates the second law of thermodynamics, we call this as a perpetual motion machine of second kind. Now, we will go to the next segment, that is reversibility and irreversibility. One thing we can derive from the Kelvin-Planck statements, that cyclic work is always less than or equal to 0. Now, here there are two possibilities in these equations. If you say that there is some internal reversibility, there is some internal irreversibility, then the cyclic work is always less than 0. But if there is no internal irreversibility, the cyclic work is equal to 0. So, this particular Kelvin-Planck statement, that cyclic work can either be less than equal to 0 or equal to 0, it depends on the concept of reversibility and irreversibilities. So, here we define this reversible process based on the second law in such a way that one can view this reversible process is to be performed in such a way that both system and local surroundings may be restored to the initial states without producing changes in the rest of the universe. This process does not fulfill the stringent requirement, and if the process is not the process does not fulfill this stringent requirement, then it is called as an irreversible process. Of course, all natural spontaneous processes are irreversible. One can say that when a process is not reversible, the conditions that has to be satisfied is that it has to be in the system and surroundings must be in the complete thermodynamic equilibrium. By thermodynamic equilibrium, we mean that conditions of mechanical, thermal and chemical equilibrium is satisfied. Other option is that the irreversibility is that there are some dissipative effects and which are not recoverable. So, such dissipative effects include friction, viscosity, inelasticity, electric resistance, all other things. Now, we are going to talk about some of the classical thermodynamic examples that will talk about how the process is irreversible in nature. Some processes are like isothermal and adiabatic transformation of work to internal energy. So, this is a situation where work is converted to internal energy. In one case process is isothermal, other case process is adiabatic. So, in these processes we can say they are irreversible processes. And when ideal gas rises to vacuum, that means as if you can imagine that there are two gases, they are separated by a complete partitions and entire system is insulated, and if you remove the partition, the gas which is at higher pressure will rush into the gas which is at low pressures. So, this process we call as a free expansion process. That means one can say that ideal gas, it is as if you can view this gas rushing to a vacuum. There is a tremendous pressure difference between them through a partitions. Other type of processes like throttling process, which is an irreversible process. All chemical reactions, phase change process are considered as irreversible process. Diffusion of gases, mixing of different phases of matter are also considered as a irreversible process. Now, after complete understanding of reversible process and irreversible process, concept of work and heat, now we are in a position to define a heat engine. Now, this heat engine is based on the fundamental cycles and what we call it as a Carnot cycles. So, this Carnot cycle, when it is introduced to give the concept of engines, which means that the conversion of heat to work has to be done through a device which is called as heat engines. And this conversion has to take place between two temperatures reservoirs, one at high temperature which is called as source, other is at low temperature which is the sink. But here there are some important question mark that remains, that what is the maximum thermal efficiency of the engines for a fixed operating temperatures between source and sink, what is the characteristics features of the engine, what is the effect of nature of working substance, because we say that there is a cyclic device which takes the heat which converts heat to work. So, these questions needs to be answered, and this answer is possible by drawing a Carnot cycle. So, a Carnot cycle is proposed consisting of set of processes that are performed by the thermodynamic systems. By this we mean that it is either a hydrostatic systems, chemical system, electrical systems or magnetic systems. The system and the working medium is imagined to be the thermal equilibrium with the reservoir at low temperatures. So, this is the another assumption that we make. Now, when you say that a Carnot cycle, we say there are four processes that occur in the Carnot cycle. The first one is a reversible adiabatic process that occurs in a direction to rise the temperature to high temperature reservoir. That means there is a reservoir which is at high temperatures and the process has to proceed in a direction to reach this temperature Th. The working substance is maintained in contact with that reservoir Th, and a reversible isothermal process is performed in such a direction, so that fixed amount of heat QH is absorbed from the reservoir. The third process is a reversible adiabatic process, which is performed in the opposite direction of step 1. That means, wherever, that means we should, this process should proceed towards the low temperature reservoir, so that temperature drops. And the fourth process is the working substance is maintained in contact with the low temperature reservoir, and the reversible isothermal process is performed in opposite direction of step 2 until the working substance and the surroundings are at their initial states. So, during this process the fixed amount of heat QL is rejected to the low temperature reservoir. So, these are the statement of all the 4 processes in a Carnot cycle. Now, let us see how these 4 processes are represented in a graphical form. Here there are 2 figures which I shown here. From the first one, we say that Carnot cycle is drawn for a real gas. So, what we draw is that process 1-2, which is a reversible adiabatic compression process. Process 2-3 is reversible isothermal expansion. Process 3-4 reversible adiabatic expansion, and process 4-1 reversible isothermal compressions. And of course, all the processes are quasi-static in nature. So, this is done for a real gas. Now, you can think about a cycle, Carnot cycle, which is operated for a mixture of liquid and vapor. So, when I say liquid and vapor, we draw 2 limits, that means LA and LB, that means we draw one vertical line LA and LB. So, that means in this region, this state of the system is completely liquid, and there is a region beyond VA and VB. So, in this region the state of the system is completely vapor, and we are operating the Carnot cycle between these 2 lines. And in fact, this is nothing but the concept of Rankine cycle, where the cycle is operated between 2 lines, liquid lines and saturated liquid line and saturated vapor line. So, that is a different segment, but here if you want to draw these particular processes, what you call is that process 1-2 is a reversible adiabatic compression, 2-3 is a reversible isothermal, and this process 2-3, since it is a phase change process, we say it is isothermal as well as isobaric process, and this process is known as vaporization. Process 3-4 is a reversible adiabatic expansion, and then 4-1 is again isothermal condensations, and this isothermal condensation process is also in isobaric nature, because these 2 processes, that is 2-3 and 4-1, they occur at same temperature and pressure. Okay. Then having said this, now we are going to come back again to Carnot refrigerating systems. That means, how that similar concept of Carnot engine is going to be extended for a situations if it is a refrigerators. So, when you say Carnot engines, it takes it produces W amount of heat, and we will say Carnot refrigerator, it takes W amount of heat to transfer heat from the low temperature reservoir to high temperature reservoir. Now, from this entire Carnot cycle analysis, we can frame some inferences. First one is Carnot theorem. It says that, it states that no heat engines operating between 2 reservoirs can be more efficient than a Carnot engines operating between same 2 reservoirs. So, we will prove this, that what it means is that if a Carnot engine is operating between 2 reservoirs, that is temperature TH and TL, then any other heat engines cannot have efficiency more than this Carnot engine. A corollary to this Carnot theorem is that all Carnot engines operating between two reservoirs have same efficiency. That is quite obvious. The maximum thermal efficiency that can be achieved by a heat engine operating between two reservoirs at different temperatures is the efficiency of the Carnot engines with same temperature limit. The essential characteristics of the Carnot engine is that it is reversible and operates between two reservoirs. The superiority in the efficiency is mainly due to the fact it absorbs all the heat at higher temperatures. That means, we imagine this absorption of heat to occur in a very quasi-static manner, or in this case in isothermal manner. So, that temperature of the highest temperature of these things does not change. That means, and all the heat gets absorbed by the engine, and it rejects also in similar sense, it also rejects that rejects all the heat at low temperatures. And moreover, we are subsequently we are going to say that we are going to prove that the Carnot engine is independent of working substance of the system. So, now we will try to move to next segment, and which is called as thermodynamic temperature scales. Now, to prove these things, that means, we always say that there is a high temperature reservoir, there is a low temperature reservoir, and some heat is taken from high temperature reservoir and rejected to low temperature reservoir. So, what is the correlation between this heat and the temperatures, and that too it is whether it is reservoir dependent or not, whether it is the working fluid substance dependent or not. So, to bring this ambiguity, we are now going to define a scale and what we call as a thermodynamic temperature scales. So, to prove this, we consider a Carnot engines that absorbs QH amount of heat from a reservoir at temperature TH and rejects QL unit of heat to the low temperature TL, and of course, it has an efficiency which is independent of working substance. This we are going to prove. So, to consider this, let us view this particular explanation in this manner. So, we can say that we have a high temperature reservoir and which is maintained at TH, and there is a low temperature reservoir which is at TL. Now, we imagine that one engine which is nothing but a reversible engine, that is RA, which operates between TH and TL, and let us say it takes Q1 amount of heat and rejects Q2 amount of heat, and thereby it does WA amount of work. Okay. Now, within the same temperature limit, we can also have multiple number of Carnot engines. That means, one can think of another reservoir which operates in between, and this reservoir is at T2. So, let us put this TH will represent as T1 and this TL represent as T2, and in between we have another reservoir T3, and we can frame this another heat engine which takes Q1 amount of heat and rejects Q3 amount of heat, and thereby it does WB amount of work. Now, between the reservoir T3 and T2, we can have another heat engine, reversible heat engine RC, that delivers Wc amount of work while taking Q3 amount of heat and rejecting Q2 amount of heat to the temperature Tc. So, if this is the explanation that we gave, that we can, that means in other words we can say there may be infinite number of reversible engines that can be operated between the temperature T1 and T2. So, here we make a conditions that for a 3 temperature reservoir T1, T2 and T3, T1 greater than T3 greater than T2. What we can write that for a reversible engines, we can write efficiency of the reversible engine, that is 1 minus QL by QH. So, in other words, we can represent these particular equations as efficiency in a functional form, that is phi as a function of TH and TL. Now, from this equation we can find another expressions, that is QH by QL as a function of TH by TL. So, basically what we are writing this particular equation in a functional form. So, that means QH by QL in a function of TH by TL. Now, here we will try to impose the situation that a Carnot engine operating between 3 reservoirs T1 greater than T3 greater than T2, we can think that there is a engine A, RA, which is operating between T1 and T2. So, we can write Q1 by Q2 is a function of F T1 and T2. Another engine that operates between T1 and T3. So, Q1 by Q3 is a function of T1 and T3. For engine C, this Q3 by Q2 is a function of T3 by T2. So, if you take this ratio, what it turns out to be is that the functional form F T1 and T2 is equal to F T1 T3 and F T3 T2. So, here you can see that we have equations, and in the left hand side of the equation there is no term T3, but where in the right hand side term there is a function, there is a term T3. So, we can say that these relations exist in such a way that the T3 vanishes while taking this ratio, and so that means since this functional relations are arbitrarily chosen, so T3 should vanish. So, in other words we can write F T1 and T2 is a nothing but the ratio of some other function psi T1 divided by psi T2. So, by this concept we can now write this particular equation in this manner, where we would say Q1 by Q2 is equal to psi T1 divided by psi T2. And here if you choose the functional relation in such a way that simplest one will be a linear relations. So, if I can say that we choose the relation in such a way that the ratio will choose in which should be the ratio Q1 by Q2 should be equal to the T1 by T2, and such a situation we call this as a ratio of thermodynamic temperatures. Now, let us see what is its significance. Now, when we say this Q1 by Q2 as a function of T1 by T2, it means that we are now correlated, that we have temperature T1 and there is a engine, and there is a low temperature T2. So, it is a source and it is sink, and we have Q1 amount of heat and it is goes as Q2 amount of heat by virtue of this work that is going out as W. Now, we have now framed this equation Q1 and Q2 this ratio and Q2 by T2 this ratio, and this functional relations becomes a linear relations that is T1 by T2 with certain conditions, and that conditions we are going to establish such a way that the one of the important relations will remain, that it has to be Q1 by Q2 is equal to T1 by T2. Now, under what circumstances this relation is valid? So, this we are going to prove. So, for that what has been chosen is that we take some kind of temperatures, and this temperature has to be a T2. We can bring it to a temperature which is nothing but the triple point of water, for which we know what is the value of heat transfer, that is during when the heat is rejected to at a temperature which is nothing but the triple point of water, and that point of time what is the amount of Q. So, this will give you the basic definition of another temperature at the which is called as absolute temperatures. Now, that absolute temperatures, when you say triple point of water, there it is, we can say that all the three matters coexist. That means, if you take water at maybe 273 Kelvin, we can say that solid, liquid and vapor, all the three phase coexist. At that point, the choice of working substance becomes now independence. So, this is the essential concept of definition of an absolute scale. So, if you try to correlate with what temperature what we have studied while talking about zeroth law of thermodynamics, we said that there is a temperature scale which depends on the specific working substance. For example, when you say gas thermometer, when you say mercury thermometer, so all these things are essentially dependent on the working substance, whether it is a mercury or it is a gas or any other substance. So, zeroth law of thermodynamics, when it gives the concept of temperature, it always relates with the nature of the working substance. But here when you deal with the Carnot cycle and the thermodynamic temperature scale, we are going to choose a temperature scale in such a way that relation between Q1 and Q2 are linear. At the same time, the choice of working substance is independent, and for under such circumstances we say that we write this Q1 by Q2 relations in a form that if you take the triple point of water, which is nothing but 273.16 Kelvin, where the choice of working substance becomes independent, that point T becomes 273.16 Q by QTP. And this now in these equations, if Q is equal to QTP, then this will imply T is equal to 273.16 Kelvin, and this is nothing but your absolute temperatures. So, definition of absolute temperature can be written like this, and this definition we get it from the Carnot theorem from the Carnot cycle informations. So, what does it say? That when a system undergoes a reversible isothermal process without transfer of heat, then the temperature at which it takes place is called as absolute temperature. Now, at this point there is no concept of isothermal or adiabatics, all are identical, and here the choice of unit, which can be either Kelvin or Rankine. So, many times like the standard practice that we are using the SI system of unit, that is Kelvin, and if you go for the British systems, it is referred as Rankine. Now, at this particular point we are now able to define an efficiency what is called as Carnot efficiency. So, the if you look at this particular equation again, that for a reversible heat engines we can write this expression of efficiency as eta r is equal to 1 minus QL by QH. Now, putting QL and QH is equal to TL by TH, we can write For a reversible engine, this efficiency comes as a ratio of 1 minus T L by T H, and here the temperature has to be expressed in a absolute scale. Now, in this equation what we can say, when the T L goes to 0, when T L goes to 0, which implies efficiency of a reversible engine goes to 100%, and T L goes to 0 means it is a almost impossible situations. T L is 0 means we are going to absolute 0. So, it is almost an impossible situations. So, the Carnot engine can never have 100% efficiency. That means, in other words, T L must have a finite value. Then if you go to the reverse process, reverse concept, then you can say that for the conversion of heat to work is possible only when there is a rejection of heat to the low temperature sink. So, the nature does not provide any reservoir with absolute 0 temperature, that is, a heat engine with 100% efficiency is a practical impossibility. So, the definition of absolute 0 holds good for all substance, and therefore, it is independent of specific properties of any arbitrary chosen substances. So, with this we come to the end of this module 1, but before I conclude, I will just try to give some fundamental concept which are left out in this lecture. First is that prove the equivalence of Kelvin-Planck and Clausius statement of second law of thermodynamics. So, I have already mentioned that if one of this statement is invalid, that means if Kelvin-Planck statement is invalid, other is also invalid, that means Clausius statement is also invalid. So, to do that, let us recall our figure which I have shown earlier, where it is said that in the first case we have this a refrigerator and other one is heat engine. So, first of all let me put K as Kelvin-Planck statement, and if it is false, then I will put it as a minus K. So, that means, if the Kelvin-Planck statement is false, I will write it as a minus K. Similarly, C stands for Clausius statement. So, I will put minus C as false if it is if the Clausius statement is false, is not satisfied. So, since the second law of thermodynamics is the negative statement, so we will try to interpret if you try to interpret equivalence between K and C. In other words, I can say if K is true, then Clausius statement is also true. Otherwise, if K is false, then negative statement of Kelvin statement is false, then Clausius statement is also false. So, all these things should also hold good. So, this is true statement and this is false statements, okay, and this has to be proved, and which we call as equivalence between Kelvin-Planck and Clausius statements. So, first thing, we consider a refrigerator that takes QL amount of heat and also rejects QL amount of heat to the high temperature reservoir, and in this process it does no work. That means, we can say we are now violating of Clausius statement. So, I will put it as minus C. Violation of Clausius statement means it is minus C. Then we can for the in the same concept with between same high temperature and low temperature reservoir, we are putting an heat engine that takes QH amount of heat and rejects QL amount of heat. So, that means rejects QL amount of heat to the low temperature reservoir, and as a situation we say operation of heat engine which is true. Now, but globally if you see, if you take both refrigerator and heat engine together, what you view is that combined machine takes QH minus QL amount of heat and produces W amount of, that is nothing but QH minus QL amount of work. But while doing so, it does not reject heat. So, this means it is a violation of K, that is minus K. So, in other words, it says that violation of Clausius statement also is the violation of Kelvin-Planck statements. And a similar logic we will put in a reverse way, that is, let us see that we have a heat engine that takes QH amount of heat, but no heat is rejected. So, for this, which means no heat rejection means violation of Kelvin-Planck statement. Means violation of Kelvin-Planck statements. So, I will put it as minus K. Now, while doing so, we can also think about another refrigerator which takes QL amount of heat and rejects QH plus QL amount of heat to the high temperature reservoirs. Now, in this process, if you join both heat engine and refrigerators, so we say that then we have operation of refrigerator, then for combined system it takes QL heat, does W work, and reject QH plus QW. So, this will imply violation of Clausius statement. So, from this we can say we started with violation of Kelvin-Planck statement, we proved that violation of Clausius statements. So, in other words, these two possibilities is never possible. When this negative statement is proved, in other words, there is a equivalence between Kelvin-Planck and Clausius statement, K is equivalent to C. Now, in another similar problem, one of the corollary of Carnot cycle is that always a reversible cycle is more efficient than irreversible cycle when they operate within same two reservoirs. Now, to prove that, we can say, we assume that there is a hot reservoir which is at temperature T h and there is a cold reservoir which is at temperature T L, and in between we can imagine that there is a reversible engine R and there is a irreversible engine I. Now, when I say reversible engines, the heat transfer is Q s and heat rejection is Q c. Heat transfer from hot reservoir is Q s and heat transfer from the to the low temperature reservoir is Q L, and both the process is possible. Either we can give W R amount of work to this reversible engine, take heat Q c from here and reject Q h to here. Other way, in heat engine mode, the engine can operate with W R amount of work while taking Q h amount of heat from the source and Q L amount of heat, Q c amount of heat to the sink. So, this is how a reversible engine operates, but in irreversible engines both this system is not possible. So, I can say it only gives in one mode, that is, we get W I amount of work while taking heat Q h amount of heat and rejecting Q dash h amount of heat to the sink. So, since these are reversible and heat reversible engines, to prove this fact that reversible cycle is more efficient, then we have to recall Kelvin-Planck statement. So, this Kelvin-Planck statement in a mathematical form we write that W cycle is less than or equal to 0. Now, in this, when you apply this particular concept for a combined system which includes this reversible engine and irreversible engines, we can view this through a dotted line of these combined systems. We can write W I minus W R is less than 0, because entire dotted line systems is nothing but is irreversible. And so, we can write W I is equal to W I minus W R is equal to 0. So, in other words, we can say W I, that means work transfer in an irreversible engine is always less than work transfer in the reversible engines. So, from this is the proved, but what we have asked for efficiency. So, you can rewrite these expressions, like if you say reversible engine W R, we can write W R by Q H, and irreversible engine eta I is equal to W I by Q H, and Q H is same for both the cases. So, and W I is less than W R. So, it means reversible engine has higher efficiency than irreversible engines. Another concept, that is first statement. Second concept would be that if when we say reversible and irreversible engines, if both are reversible engines, then we can say W R 1 is equal to W R 2. So, assume that I is replaced with W R 2 and R is reversible engines is replaced by W R 1. What we are trying to prove is that if both the engines are reversible, then the efficiency of reversible engine R1 is also equal to efficiency of the reversible engine R2, which means all the reversible engines operating between same two temperature limits have same efficiency. That is first, the second statement. First statement was, if reversible engine has always higher efficiency than the irreversible engines. So, these two statements are nothing but corollary of second law of thermodynamics, or we can say Carnot theorem. So, with this I conclude this lecture for today. Thank you for your attention.